All right, this video is going to be the beginning of chapter 5 in your book presently, and it's going to be talking about a probability distribution table. Now, this probability distribution table is going to look a lot like a frequency distribution table. It's going to be a 2-column table. So I'm going to share my PowerPoint with you and kind of talk you through it. All right, so like I said, it's going to look a lot like a frequency table because it's got 2 columns. The difference is going to be your left column is going to be your sample space. So it's all the things that you could get. And then your right side's not your frequency, it's your probability of each one of those happening. So for instance, what if it said construct a probability distribution table for rolling a die? Now think about when you roll a die, what are all the things that are on a die? 1, there's a 2, a 3, a 4, a 5, and a 6. So that's why those values are listed under X, because that's all the things that you can get when you roll a die. That's the sample space for rolling a die. Now, if you roll a die one time, what's the probability that you're going to roll a 1? Remember, on the bottom of a probability is your total. So there are 6 things on the die. How many 1s are there? 1. Okay, what's your chance of rolling a 2? Well, again, there are 6 things on the die, but there's only 1 2. So since there's 1 of each one of these, your chance of rolling a 3 is 1 out of 6, and your chance of rolling a 4 is 1 out of 6, and so forth for 5 and 6. Now, these probabilities will not always be the same number on every problem. They're just the same on this problem, because when you're rolling a die, you have the same chance of getting any one of those numbers, those integers from 1 to 6. Now, for it to really be a probability distribution table, there are 3 conditions, 3 requirements, because sometimes it'll look like a probability table, but it's not. And these are your 3 conditions. Under X, these have to be numbers, so there can't be words. So the X values, the sample space have to be numbers. The other thing that's a big deal is when you add the probabilities up, you have to get exactly 1. So think about it, 1 over 6 plus 1 over 6 plus 1 over 6 plus 1 over 6 plus 1 over 6. Remember, you have to have a common denominator when you're adding fractions. So if I added that up, all right, my common denominator is 6. And then I add up the numerators, 1, 2, 3, 4, 5, 6. And sure enough, 6 divided by 6 is indeed 1. So when you add this probability column, you've got to get exactly 1. Now, a word of caution. If you took 1 on your calculator and you divided it by 6, it's not going to come out pretty. It ends up being about, and you get a decimal and you get a 1, and then the 6's just keep repeating. So if you were to change this fraction to a decimal, and you say, well, that's about 0.1667, then you've got a little bit of error. And if you get a little bit of error in these, when you add them, you might not get exactly 1. So do notice, if you round off, you might not get exactly 1. You should get really close though. So one of the things they're going to ask you is is this a probability table? And one of the ways you'll check it is you got to add this second column up and you got to get 1. Now, this third thing, remember, is just a reminder. All probabilities, remember, have to be between 2 numbers. And on your test, I'm probably going to ask you, probability is always a number between blank and blank. What goes in those blanks? 0 and 1. So it's reminding you that all probabilities have to be between 0 and 1. So you'll never have negative numbers in this column, and you'll never have numbers bigger than 1 in this column. So that's just kind of a reminder. All right, so those are your 3 conditions for a probability table. So look at this next one. Part of your homework is going to be asking you determine if you've got a probability table or not. So one of the things you notice, all right, which one of these can you rule out already that's not going to be a probability distribution table? All right, how do you know this third one cannot be a probability distribution table? Because remember, one of your conditions is this left column has to be numbers, and these are not numbers, so this one's not a probability distribution table. It's a table with probabilities, but it's not a probability distribution table. Now, these both have numbers here, so that's check. All right, so that first condition checks. All the probabilities are between 0 and 1, so that checks. So condition 1 back on your previous step, so condition 1's checking and condition 3 is checking. But now I got to go check condition 2. So take your calculator and add these numbers and see what you get when you add them up. So when you add those probabilities, see what you get when you do that. All right, did you get exactly 1 when you did that? Okay, well, if you got exactly 1, then yes, this one is a probability distribution table. Now this one looks like it, but when you add this decimal and this decimal and this decimal and this decimal, so kind of stop the video and add them. All right, what'd you get? Did you get like 0.989? All right, well, that's not 1. So again, no, that's not a probability distribution table. And then no, that one wasn't. So sometimes you can tell by glancing. Sometimes you can't tell by glancing. Okay, so you're going to have to add up those probabilities and make sure that you get 1 when you do that. Now, if you get 0.9999 or 1.0001 and they've converted fractions to decimals, it might just be a rounding problem. But on the test for me, on your midterm, if it's not exactly 1, you say no. Okay, in the book, sometimes if they're close, they're good. But with me, exactly 1, yes. If it's not exactly 1, no. Now, I'm going to ask you to do a couple of things to a probability distribution table. All right, I'm going to ask you to find the mean and the standard deviation. So remember, another thing you're going to have to do is you're going to find the mean and standard deviation of a frequency table. And those formulas are on your formula sheet. So make sure you can do that. Another thing you're going to have to be able to do is you're going to have to be able to find me the mean and standard deviation of a probability distribution table. So let's go look at how you do that. And these formulas are in your book and they're also on your formula sheet. So you don't have to memorize the formulas. So remember, this mu stands for mean of a population. So the reason they're doing this symbol instead of X bar, this is your sample space. So this is all the things that you could get. Okay, and this is the formula. Now remember what we said. X is always your data in every formula the whole semester. So these are your X's. Now P of X are your probabilities. So look what this says. Remember, we go inside to do our bracket first. It says take every X and multiply it by its probability. Okay, so I've got to say 1 times this 1/6. So 1 times 1/6. I've got to say 2 times this 1/6. So 2 times 1/6, and 3 times 1/6. And then I've got to say 4 times 1/6. And then I've got to say this X times its probability. So 5 times 1/6. And then I got to say 6 times 1/6. Now, what do you do when you're multiplying a whole number by a fraction? You have to have fractions, not whole numbers. So how can you make any number a fraction? Can't you put it over 1? So I can go up here and put all of these numbers over 1. All right, then I've got a fraction times another fraction. Now remember, what do you do when you have a fraction times a fraction? Multiply the numerators together. So 1 times 1 is 1, and the denominators, 1 times 6 is 6. So 2 times 1 is 2, 1 times 6 is 6. 3 times 1 is 3, 6. So 4 times 1 is 4, and 1 times 6 is 6. Now, what does this funny looking symbol right here mean? Well, after you do all that multiplying, you're supposed to add all those answers up. So I'm going to add all of those answers that I got. Now remember, when you're adding, you have to have a common denominator. You don't have to have a common denominator when you're multiplying, but you do when you're adding. And I've got a common denominator, so I'm not going to reduce anything yet. So I keep that common denominator of 6 and I add 1 plus 2 plus 3 plus 4 plus 5 plus 6. So when you add those numerators, you get 21. Now remember, I either want a reduced fraction or a rounded decimal. So I would not take this fraction right here because it's not reduced. You can divide the numerator and denominator both by 3. So if you divide both sides by 3, now remember what you're really doing, 3/3 is a really strange way of writing a 1. And when you divide a number by 1, it doesn't change the number. So that's why this fraction and this fraction have the same value. So that's how I reduced it to 7/2. And then most of you tend to like fraction, decimals better. So the decimal equivalent of 7/2 is 3 1/2. So what does that mean? Now remember what I told you we're doing. We were rolling a die. So remember what mu stands for. Mu stands for mean, and mean is another way of saying an average. Now, can you really roll a 3.5 when you roll a die? No. You know, you might roll a 2, and the next time you might roll a 6, and then you roll a 1, and you roll another 2, and then you roll a 4, and then you roll another 4, and then you roll a 3, and then you know, you just keep rolling and rolling and rolling. So dot, dot, dot. How do you get a mean average? Don't you add them all up and then divide by how many times you roll? So if you roll this die over and over and millions of times, the average would be about 3.5. Okay, that's one of the reasons that in a lot of dice games, when you're rolling a pair, all right, you're trying to get 7. A lot of games win when you hit a 7, because if the average roll for each one is 3.5, then of course, you know, your average roll for the pair. All right, but that's how you find the mean of a table. You simply use this formula. You say every X times its probability, and you just add those answers up and then make sure you reduce it. Very simple. Now, how do you find the standard deviation of a table? Well, if you've got a probability distribution table, the way you find that standard deviation is this is your formula right here. And again, it's on your formula sheet, so you don't have to memorize it, but you do have to understand it. Now, the first thing I want you to notice is built into this formula is the mean. So before you can do standard deviation, you have to do mean, even if they don't tell you to. Okay. So back over here, remember, let me kind of go back over here. If I were doing the standard deviation of this table, I'd have to use this 3.5 in my formula. All right. And a lot of times they'll ask you to do both. All right, so it's not a problem, but I do want you to know. So if you miss the mean, you're automatically going to miss the standard deviation. So you got to be real careful. So let's go get the mean first. Now remember, how do we do mean? Remember, to get the mean, remember what your formula was. It was the sum of X times P of X. That's how you find the mean. So you got to say this X times that probability, and this X times that's probability, and so forth. So I've got to say 2 times that number and 3 times that number. So I've got to say, so I wrote that down here. You can freeze it and copy it. You should be taking notes, remember. Well, remember, 0 times anything is 0, and 1 times any number is that number. And 2 times 375 hundredths ends up being 75 hundredths, 375 thousandths. And 3 times 125 thousandths is 375 thousandths. So then remember, what does that funny looking E mean? It means to add, to sum. So after you do all your multiplying, then you add those answers up. So if you add those answers up, you get 1.5, 1 5/10. So that's why right here, that little symbol right there, that symbol is going to get replaced with 1.5. Now I've got to go do this part. All right, so let me kind of clear it so there's not all this writing. I'm going to go do this part now. All right, I've already done that part and put in my 1 5/10, but don't lose your square. You got to square that in a minute. Now I want you to notice, remember what your formula was for mu. All right, this was your formula for mu. So this box looks almost like this box. So be careful. The only difference is here, there's a squared. So remember your order of operations. I've got 2 things inside this parenthesis. I've got an exponent and a multiplication. So remember, by order of operations, I've got to do the exponents first. So I've got to square the x's before I multiply. So I'm going to square this 0 first, and square that 1 first, and square that 2 first, and square that 3 first. So when you square 0, it stays 0. When you square 1, it stays 1. But when you square 2, it turns into a 4. And when you square 3, it turns into a 9. So I'm going to say 0 times that number, that gives me 0. I'm going to say 1 times that number, and that gives me that number. But I'm not going to say 2 times that number when I'm doing this one. I'm going to say 4 times that number. So I get 1.5. And I'm going to say 9 times that number. Okay. All right. This should be, sorry, that's a misprint. That should be a 0.125. So fix that in your notes. All right. That was a mistype typing there because that number is the same. All I should have changed was 3 squared to 9. Okay, so we double check it and make sure I wrote it down right. So 9 times 0.125 should be 1.125. So that is correct. So when I add all these answers up, I get a 3. So that 3 replaces this box. So that's where I got that 3. That 3 was the sum of every squared number times its probability. Now remember, order of operations, do you subtract or do you do exponents? You do exponents first. So you're going to have to square this 1 5/10 first. Then when you subtract that from 3, you get 75 hundredths. And then your last step is to take the square root of that. So you get about this number. And I don't really care where you round, just don't chop it off. But probabilities, remember, I want to 3 or 4 decimal places. Mean and standard deviation, I don't really care. Okay, so 3 or 4 decimal places. So that's how I get standard deviation. Now, if they wanted variance, remember how you get variance? You take your standard deviation and you square it. So you would take that 0.866 and you would square it. All right, so if they asked you for variance, let's see what that would be. That would be about 0.75, all right? All right, so if they wanted variance. But I think on most of your homework, they're just gonna want mean and standard deviation. But you know of how to get variance if they want it from standard deviation. So that's the 2 things you've got to be able to do to a table, or 3 things. You got to first decide if it's really a probability distribution table. Remember, add the probabilities, make sure they're 1. Make sure you've got numbers in your X column. Okay, then make sure you can find the mean. All right, so remember, there's your formula for mean. It's on your formula sheet. You got to be able to find standard deviation, and there's your formula for standard deviation. Now, the one other thing they might ask you to find is they might ask you, give you a problem and say, what's the expected value of this problem? Well, what only thing you really have to remember is this: expected value is exactly the same thing as the mean of a probability distribution table. So on your formula sheet, okay, they just have the same formula kind of written 2 ways. So because it's the same, E is the same formula. So E and mu of a table are the same thing. Now, so look at this problem. You're going to buy a lottery ticket. Okay, so the lottery ticket is a 3-number ticket. Remember, you go to the convenience store, okay, and you're going to pick 3 numbers, and they're double digits. So remember, every number can be 0 to 99. All right, so you're going to get a 3 double digit, all right, number. Okay, so you might pick, I'm going to pick 66 here, and then I'm going to pick a 17, and then I'm going to pick a 24. So it might be when you go home, your number's like 66, 17, 24. So you're picking 3 2-digit numbers. Okay. All right. So you're going to buy 1 ticket. If you win $50,000. And it costs you $5 to play. So they want to know what's your expected value. So expected value would be your average winnings if you played this game like 1,000,000 times. Millions just over and over and over. What would your average be? Okay. So most people, since you're used to doing the mean of a probability distribution table, most people are better off kind of making a table and doing it from there. So think about it. If you play this game, what's all the things that can happen to you? I mean, either you win or you lose. So if I make a table, that's why I put either I win or I lose. Now remember what I've got to have. I've got to have the probability of each. So I went over here to the side and decided, how do I find the probability of winning? Well, remember, I'm buying 1 ticket. So I know what number to put on 1. I've just got 1 chance of winning. All right. So 1's on the top. The problem is I don't know the total. I don't know how many different tickets there would be. So this goes back to that last section on finding a total when you don't know. So order matters in a lot of games. If order does not matter, remember you would use combinations. But if order matters in this lottery game, then what you would do is, remember, I could use the counting principle. So what I did was I kind of drew 3 blanks. Now remember what I said, every blank is a double digit. So in every blank, I can do 0 to 99. So that's 100 possibilities here. When I go pick the second number, if I want to repeat the number, they'll let me. So I can pick like 99 here and 99 here and 99 here if I want to. So I'm going to have 100 choices for each of these blanks. So that's why there's 100. Remember the counting principle, you multiply times 100 times 100, which is a million. So now my bottom is a million. So I've got a 1 out of a million chance of winning. Boy, don't I feel lucky. Okay. So I've got a 1 out of a million chance. Well, now remember, either you win or you lose. They're complements of each other. So remember, how do you find complements? So the probability that you do not win, remember, is going to be 1 minus the probability that you do win. Remember, that's how we do complements. Now, what's the same thing as not winning? Losing. I could have put win and not win, but most of us say lose. So if I do 1 minus 1 over a million, all right, you know, so all I did here was change my fraction to a decimal. So if I do, I can do 1 minus the fraction, or I can do 1 minus 0.0000001. And that's where I got this number. So your chance of losing or not winning is 1 minus the chance that you do win. So notice what happens. When I add these, if I add them up, I get exactly 1. Now, the reason this isn't a probability distribution table, remember, I can't have words here. So I've got to change somehow to numbers. So what I did was I went and looked what happened with the money. If I win, now my prize is $50,000. So why don't I have 50,000 right there? Well, that's because I paid $5 to play the game. So if I subtract the $5 that I paid, I'm really only this much richer because I'm taking off what I paid to play. So really my bank account's only increasing by this much money because I paid the $5. So it's kind of your profit that goes here. Now, what happens if you lose? Well, you lose your $5. So that's why I made it a negative $5. So now this is a probability distribution table. So you know how to do a probability distribution table. All right, you do X times P of X and then you add them up. So I do this number times this number. See, that number times that number. And then I do this number times this number. So it's a negative, remember. So this number times this number gets this on my calculator, double check it. Remember, a negative times a positive is a negative. And when I add this positive and this negative, I get this number. Now, what does that mean? That's the average. So on average, you're going to lose $4.95 every time you play this game. So now, would you really lose $4.95 any single time? You know, you play it one time and lose $5. You play it another time and lose $5. You play it another time and lose. You'd probably keep losing $5 for like years. You know, and after a while, you might actually win your $49,995. And then because you're not bright, or like, you know, you might keep playing and keep losing. Now, how do you find a mean? Don't you add all those up and divide by how many times you played? This would be the average. So is this a smart game to play? Not really. Because generally speaking, you're going to lose way, 1 out of a million. What if you buy 10 tickets? Ooh, now your chance of winning is 10 out of a million. I mean, don't you know? No, just stop. Okay. So think about, when would a game be fair? What is it? What does it mean when a game is fair? All right, when a game is fair, doesn't it mean you'd win about as often as you lose? So do you understand that for a fair game, the expected value would be 0? Because you'd win about as often as you lost. So when you want to play a game, it's when the expected value is greater than 0. When it's positive, that means you win more often than you lose. So when you go to the casino or you play the lottery, those are not fair games. They can't be fair. It's a business. If it was fair, then they would make 0 money. Their expected value would be 0, and you can't run a business if you're not making any money. So they're not, they never said they were fair. Okay. So make sure that you're clear about that. So you can go play the lottery. It's just not a bright game to go play. Okay. So that's how you do it. So make sure that you can tell whether a table is a probability distribution table. Make sure you can find the mean and standard deviation of those tables. If you have any questions, then make sure that you contact me. Hope you have a great day.